HPC centers deploy a variety of scientific software, but the complexity of building scientific applications makes package management increasingly difficult. It's time-consuming and inefficient. Large-scale supercomputer codes can have hundreds of dependencies. They may need multiple versions of MPI, the message passing interface. They may need multiple versions of dependencies. They have to be built for different compilers, for very exotic architectures, and they're generally extremely hard to build. Spack is a deployment tool we developed that assembles those components and ensures that they are properly linked and optimized for any machine. In other words, Spack simplifies build processes. It speeds up installation and manages multiple configurations efficiently. Traditional package managers can't manage simultaneous installations of multiple versions and configurations. Spack is customizable and handles combinatorial builds. Spack provides a language that allows developers to describe how software packages should be built, as well as a language that allows users to describe what they want installed. Together, these languages allow Spack to customize the build for the user's needs and for specific environments. Spack can be used on supercomputers, or on a laptop, or on anything in between.
Spack contains more than 3,000 packages templated by their build options. Think of it like an app store for supercomputers. Writing package recipes for Spack is simple. Each recipe is a Python script for installing the package. Spack provides the model and abstractions so developers can easily template these recipes for every possible build option. Developers can write their own packages or easily leverage the hundreds of thousands of lines of code that others have written. Ultimately, users can assemble hundreds of libraries in just minutes, so they have more time to focus on their scientific research.
Ever since we released Spack as open source, development and use have grown dramatically. Our user community is huge and global. Spack has over 350 contributors from other labs, academia, and industry. Over 1,000 users browse the Spack documentation website every month.
Thanks to community contributions, Spack has grown to accommodate a wide range of use cases. We incorporate dozens of community suggestions and changes into the Spack code every week. The Spack team gives tutorials and workshops at a number of high-profile conferences, including supercomputing. We also visit other HPC centers to learn how they use Spack, and together we brought in Spack's capabilities.
We've worked hard to broaden Spack's contributor base by integrating features for other communities. For example, Fermilab and CERN are using Spack to build high-energy physics codes that support the Large Hadron Collider. We worked with this community to implement secure binary packaging and other features. Fujitsu plans to use Spack to automate software deployment on the Post-K supercomputer at the RIKEN Center for Computational Science. RIKEN has invited the Spack team to give a tutorial for their developers and users.
Mission-driven programs across Lawrence Livermore National Laboratory are using Spack to automate software builds. For example, developers of the hydrodynamics code Ares use Spack. Ares has more than 40 dependency libraries, and the developers leverage Spack to deploy the entire stack with over a dozen compilers. At Oak Ridge National Laboratory, Spack drastically reduced deployment time on the top-ranked Summit supercomputer from 2 weeks to around 12 hours. Their stack of 1,300 packages can now be built overnight. Scientists at Los Alamos National Laboratory are also using Spack to rapidly build and deploy their production codes.
The Exascale Computing Project, or the ECP, is a Department of Energy collaboration that is a key part of deploying the nation's first exascale computing ecosystem. And by that, I mean the applications in the software stack that will deliver mission-critical science for the Department of Energy. This will enable a brand new class of computing applications that are simply not possible today. Spack is an integral part of this ecosystem because our software technology stack is very large and quite complex. We're developing almost 90 different software tools and libraries, all with different dependencies. So we will use Spack with all of these different tools to ensure that the users of our software can more easily build them in many different environments. Having a flexible and comprehensive deployment tool, such as Spack, is the best way to standardize builds in our sophisticated ecosystem.
HPC users are very demanding. Every site, team, and simulation code has its own unique set of requirements to get the best performance out of the machine. So if I had to sum up Spack in a single phrase, it would be install it your way.